Welcome to the business analytics and data mining modeling using R. So in the previous lecture we were discussing Naïve Bayes, and specifically we were doing an exercise and modeling exercise in R environment. So we were able to import the data set and then the process and some of the transformation that we did in the previous lecture. We also looked at some of the issues that we encounter related to dates and arrival and departure time, and how we were able to correct those dates that come because of the importing of data from an Excel Windows PC to our environment. And then later on we created the different time intervals based on the departure time, actual departure time. We also did our modeling exercise, the partitioning and modeling. So so we also looked at the tables, the conditional probabilities values for different combination outcome variable and predictor combination for different values, that is nothing but different categories for the predictors and the outcome variables. So we looked at all those things. Now some of these things can also be performed using a pivot table in Excel, some of these conditional probabilities. So though we rely on the computation in R using this particular function, but these are essentially the mathematical computations. Essentially the technique is more of mathematical in nature, and the probability computation or the crux of this Naïve Bayes modeling. So what we'll do, we'll export the data set that for the training partition that we have done. We have created this training partition that we have created in the Excel format. So we'll also learn how to export data into Excel format. So and then we'll do a pivot table. We'll create a pivot table and see how the same conditional probabilities that we have computed using a Naïve Bayes function that can also be done using pivot table. So let's find an appropriate folder for this first. So if this is the folder, then we can specify this name here, and as we have discussed before that we need forward slashes and not the backward slashes in our environment to be able to use the absolute path of files. So write.xlsx is the function if we want to export the data into an Excel file. So the training partition data is going to be exported here. Now we execute this line, it has been processed, and a file flight details 1 has been created. So let's open this. So this is the file. You can see first column is nothing but the serial numbers, so nothing but the indexes also. These are indices for the which were selected when we created the partition. So right now we don't need this particular column, so we will delete this. And then we have the other columns. We have the 6 variables that we require for our modeling exercise. So these are the 6 variables, as you can see here. Now to create the pivot table, we'll select the data set and including the header. So we'll select using Control Shift and down arrow. So once this is done, we can go to the insert tab within Excel, and then we can see that pivot table option there, and then here we can click on this and we'll get the drop down menu, and first option is pivot table. So let's create this. So the range is already selected. Now we want this pivot table to create it on a new worksheet, so we'll just do OK, and this is what we get. Now from here we can create pivot table for different pairs of variables. So one is flight status. This definitely has to go here, column, and then for example depending on the destination. For example, if we want to calculate values for destination, and so that we can do. So the column label is flight status, row label is destination. As you can see, a particular pivot table has been created here, you can see here, and the count is the default has been taken here for flight status. Few things will change. So for this, left click, you would see value field setting, and the value field setting, so everything is okay in this is summarized by everything okay, but show values as, there we would like to change, and we would like to make it percentage of column. So this, as you can see, once we did this, so numbers have been converted into percentages. Now we can compare this to the results that we have got in R to find out whether everything is okay or not. So you can see, let's look at the results that we had for output variable and the destination. So you can see 3 categories: BLR, Hyderabad, HYD and IXC. So numbers you can see here: 50, 29.17, 20.83. So same numbers are here. Similarly for on time, 47.5, then 30, and then 22.5. So you can see the probability computation can also be performed using we just looked at the data, created a pivot table, and we were able to compute these conditional probabilities. So the computations that we have performed using the function in R, this can actually be performed using a pivot table that are available in Excel as well. So let's move forward. Now the table, conditional probability table, if we are interested in accessing specific values. For example, in the table, if we just want to have a look at the flight carrier probabilities, conditional probabilities related to flight carrier, we can express in this format, because the tables that we have is actually a data frame list, and we can execute this. You can see that for outcome variable and the flight carrier, we have the conditional probabilities. If we want just to one first row and third value, that is the value for jet air wage. So this is how we can use the brackets notation and access this value. You can see 0.625. If we don't want to use the numbers for row and column, we can mention the name of the rows and columns also in this fashion, on time and indigo for second example. So we'll get this value 0.375. So let's execute this. You can see, so this is how we can access the values in R for the Naïve Bayes tables from Naïve Bayes tables. So let's go through an example where we will try to compute the values by accessing these numbers. So probability numbers, as we have shown, we can also be computed using Excel and R as well. We can access the individual probabilities value. Now using these value, we can now go through one example wherein I will try to compute the probability values. So this is the example. We want to classify an Indigo flight from MAA, this particular airport, to IXC, this particular airport, between 0 and 6 am on a Monday. So you can see in this example, so all the information related to different predictors is available. Now using this predictors, this information, how we can go ahead. As you know that in complete or exact base, we'll have to find the exact matches, so which we are not doing. We are going to use the Naïve Bayes computations. First let's see whether there are any exact matches or not. So we'll just look at whether there are exact matches or not. So this is how we can do this in the df train partition, and here we can look at whether the flight dot carrier is having this value indigo, and then the source and destination, and then day and departure. So appropriately we can mention the value and find out the rows. You can see this particular expression has been written in the row value, right? The column value, all columns are selected. So let's execute this. You can see 0 rows, so no such observation is there in the training partition, right? If we just change this particular value from 0, 6 to 6 and 12, let's see if there are any values. So if we just change the interval, you can see there is one value which is actually having all these. There are other predictors information are met. We have a match for other predictor information except for the departure time interval. So for that particular interval we did not have any matches, therefore complete or exact this cannot be applied. So let's come to the Naïve Bayes formula. So we are going to compute numerator value only first. So as we have discussed in Excel exercise as well, first we need to compute the probability value for delayed given the information, given the predictors information as per the example. So you can see this is how we can access. So first, proportion of values belonging to delayed class. So this is there. Then delayed and indigo and delayed MMA, delayed IXC, delayed 0 to 6 time interval, departure time interval, and then delayed on Monday. So for all these in this fashion we can actually access the individual conditional probability values, and we can multiply, and the proportion is also there. So this is how we can actually compute the value. You can see P1 has been computed. So let's print up to 4 significant digits. So this is you will get 0.0007064. This is the probability value. Now for the on time class also we can perform the similar computation. Here also, as you can see that mod, and then you can see on time proportion of records belonging to the on time class. So that is there. Then for flight carrier you can see on time and indigo. Then for source you can see on time and the MMA, this particular airport, and then the on time and IXC, this destination airport. Then the time interval, departure time interval, this is for on time and 0 to 6, and the last value, that is for Monday. So let's compute this. Let's also print the value up to 5 significant digits. So these are the values for the numerator part. So as we have done in as we have discussed before also, that if we want to compute the actual probability value, we can do so using this P1 we can divide by the summation of these two values we have just computed. So we will get the actual probability value. So these are the actual probabilities value. Now once we have the probabilities value, depending on whether we want to use the most probable class method or depending on whether we want to use the we have a class of interest, so then in that case we would like to specify a cutoff value and compare using that. So based on that we can always classify the observation. Now once we are done with our building our model using the training partition, so let's score our test partition and evaluate the performance of this Naïve Bayes model on the same. So what we are going to do here is use the predict function as we have been doing in previous techniques as well, and let's score this. So we have two options here. Type is the argument that can be used within the predict function. So if we use type as class, then we'll get the we'll get the scoring for the actual class, and if we use this particular type as raw, then we'll get the estimated probabilities value. So let's compute each of these two, actual class membership and also the estimated probabilities value. So let's look at the classification tables that we can generate using table function. So you can see actual class is stored in the flight.status for test partition as well, and the predicted class just now we computed. So these are the results. As you can see from this particular classification matrix, that 6 delayed flights have been correctly classified as delayed, but 13 of them has been incorrectly classified. On time, 4 of them have been incorrectly classified, but 20 of them have been correctly classified. So this gives us the idea. So you can look at 26 observations have been correctly classified and 17 observations have been incorrectly classified. This is mainly because of this smaller sample size. That is why we are not getting that good result. Now we can also have a look at the full information, the predicted class, the actual class, and the probability value and the other variables to understand what has happened in the modeling process. As per the results, you can see predicted class and actual class. You can see that these values, the probabilities here again you can see that in this case the default class for our variable we can look at here. Let's look at the default class. You can see delayed and on time. So the delayed is going to be the reference category, and on time is the main category included in the model. So we'll see these probabilities values that we see here is this is probability of a particular class belonging to on time category. So more than 0.5 value of the value is more than 0.5, so it will belong to the if the probability is such, then this is going to has been predicted as delayed if it is more than 0.5. If it is less than that, then it has been classified as on time. So predicted values also we can see here. So for any probability value that was more than 0.5, we have classified it as delayed, and the probability value of less than 0.5, this one, from this we can understand it has been classified as on time. So if we want to look at the actual classification error, accuracy and misclassification number, this is how we can do it. So a comparison between the scored values and the actual values will give us the accuracy. So that was 0.6 and error was the remaining 0.39 or about 0.4. Now we can also compare the performance of model on test partition with the performance of model on training partition. So let's score the training partition using the model itself. So the same function predict, and we can score this. We can look at the classification matrix. Here you can see many more observations are classified correctly in this case, as expressed using the accuracy and error numbers. So model is performing much better for the training partition, main reason being because it was built on training partition itself, and is performing slightly poorly for the test partition. Now this is also because of the smaller sample size that we have. Now for this model, if we want to generate lift curve, so this is how we can do it. So cases, we have how many cases? So for the test partition, if we want to generate the lift curve, cumulative lift curve. So we have the 43 observation. So let's create this. Now the values, actual values for this particular partition, test partition. Let's access them using mod test and variable. Now labels, let's change the labels because we need cumulative values for based on the actual classification of the observation. So we'll like to change the labels. So in this case delayed and on time, 1 for delayed and 0 for on time. So let's change the labels. Once this is done, because this mod test and being the factor variable, so let's convert it into numeric variable so that we can apply the operations, that is the mathematical operations. So this is, you can see now numeric variable and 0 and 1. Now we would be able to compute the cumulative values, right? So using this using the probabilities value that we have computed earlier, right, for the delayed class, right? So using this particular value and the actual class that we have just now created a variable, we can create a data frame of these two variables, and then we can sort these variables in terms of the probabilities values, the decreasing values, right? So we can, if you are interested in looking at the few values, let's look at the first 6 observation in this particular data frame. You can see probabilities value in actual class. Let's order them as we have done in previous lectures as well. So if you are again interested in looking at few observations, you can see now these values have been sorted or ordered in the decreasing probabilities values sequence, right? Now we can compute the cumulative values. So let's go through the code for the same. So the first value is going to be the same, so this is how we can do, and then for the remaining values we can run this loop wherein the previous value is going to be added to get the cumulative value. So once this is done, let's look at the range. So we have 43 cases. Let's look at the cumulative value range 1 to 19. Then as you can see, appropriately the limits have been specified and other things there, so we can generate the plot. So this is the cumulative gains curve that we have. This is the plot that we have. Now if we want to compare its performance with the reference line, so this is what it is, and let's look at the plot. So you can see this particular plot is performing better than in terms of identifying the most probable ones or most probable delayed flights. So this model does quite a good job with respect to the average case, that is the reference line as shown in the reference line, right? However, if we just look at the prior probabilities and the actual numbers that we have computed, right, the Naïve Bayes overall on comparing with the probabilities, we can find out that if we had used the Naïve rule, then what would have been the scenario, and if we applied the Naïve Bayes modeling. So you can see here, so had we classified all the observations as belonging to the majority class following Naïve rule, then every observation would have been classified as on time, and we would have had the error as just 24 divided by 64 and 0.375, right? But if we look at the training partition error that we have computed just before this, right, the training partition is model is doing good in training partition, but look at the model's performance on test partition, you see the error is 39.5, and here you would see Naïve rule, the error is 37.5. so Naïve rule is actually doing better than our model, but it is the cumulative lift curve that we saw that is giving the usefulness, that is indicating towards the usefulness of the model in terms of identifying the most probable ones, most probable delayed flights. So so this is our modeling exercise that we wanted to perform. Let's go back to our discussion on Naïve Bayes. So what we'll do, we'll discuss on Naïve Bayes a few more points. So we look at the Naïve Bayes as a technique. It's quite simple, right? Quite simple and easy to understand, because based on the probabilities values, So the interpretation is quite easy and can give us surprisingly good results in some situations, especially when that predictors independence of predictors values, that assumption is actually met. Then it can give us surprisingly good results, or sometimes even outperform other techniques. So this good performance can come, as mentioned in the first point, despite assumption of independent predictors values being far from true. So even if this assumption is not being met, even then we get good performance using Naïve Bayes. However, it requires a large number of records, because we would like to cover as many scenarios as possible, because the predictors, they are mainly categorical in nature. So therefore the different scenarios that could be there, we would like to compute most of them, so that for a new observation there is always probabilities values to compute and assign a class to that observation. So requires a large number of records. Now if we don't have a larger sample size, then few classes of predictors might not be represented in the training partition record. So in such situation, zero probability is going to be assumed, and then it would be difficult to classify that particular observation. Right. So however, I mean, this particular case cannot be handled by other techniques as well, but the situation is more complicated in Naïve Bayes, main reason being that the information in other predictors, for example, for one particular out of 4 or 5 predictors, it is just to the one predictor that is not matching, and if that is not if that is not present in the training partition, that one particular class, then the value, zero probability value, is going to be assumed, and therefore all other predictors, the remaining predictors information would not be counted, which is not the case in other techniques. Apart from this, Naïve Bayes is mainly suitable for classification tasks, as we have discussed in previous lectures as well. Another important point is good for classification, but not for estimating probabilities of class membership. So as we have talked about that in the Naïve Bayes formulation, it is the numerator that is sufficient for us to achieve the rank ordering of different classes of outcome variables, and that is what we are interested in. So the model as such will do a good job. However, if we are interested in the actual probabilities values, so then Naïve Bayes is not a suitable technique for such scenarios. So with this we'll stop our discussion on Naïve Bayes. In the next lecture, we will start our discussion on classification and regression trees. Thank you.